This morning at 6:35 UTC, a 4-ton piece of abandoned SpaceX hardware hit the moon at 5,400 miles per hour. Not a simulation, not a prediction, it happened. The impact created a new crater near Einstein Crater on the moon's western limb. The force of the collision was equivalent to the simultaneous detonation of nearly 3 tons of TNT. Over 1 million kilograms of lunar soil was thrown into the sky. A plume of dust and rock rose above the lunar horizon and was briefly visible to telescopes pointed at the right patch of sky along the western America. And the most extraordinary part of what happened this morning is not the impact itself. It is that for the first time in the history of human spaceflight, for the first time since we have been putting hardware into space, we watched a piece of our own junk hit another world, knowing exactly what it was, exactly where it would land, exactly when it would arrive, and exactly how hard it would hit. We had 1,080 days from launch to impact. One independent astronomer in New Hampshire identified the collision course. 23 scientists across multiple countries built an observation campaign around his calculation. South Korea positioned a lunar orbiter to pass within several kilometers of the stage 2 minutes before impact. NASA positioned its Lunar Reconnaissance Orbiter to photograph the site before and after. The crater is there right now, on the surface of the moon, permanent. The first human-made crater ever created on the near side of the moon with full advanced knowledge of its creation. What it reveals about hollow impactors, about lunar debris hazards, about the legal vacuum that allowed this to happen and will allow more of it to happen, is what this video is about. New here, this channel covers what is actually happening in space right now, with real numbers and real stakes. Subscribe. You will not want to miss what comes next. Before we get to what NASA found and what the Danuri images showed, you need to understand what makes this morning's event genuinely unprecedented, because the coverage so far has missed the most important context. Human objects have been hitting the moon since September 13, 1959. That was the date the Soviet Union's Luna 2 spacecraft became the first human-made object to reach the lunar surface. Since then, 67 years of space programs have deposited approximately 3,000 objects on the moon, spent rocket stages, crash-landed probes, soft-landed spacecraft intentionally left behind, scientific instruments, mission debris. The combined mass of everything humanity has left on the moon now exceeds 209 tons. 209 tons of human-made material on a world we intend to build a permanent base on. A world where NASA's Artemis program plans to put astronauts on the surface for extended rotations. A world where, within the next decade, we intend to establish crude infrastructure, resource extraction, operations, and surface habitats. Nobody is tracking most of it. Nobody is required to. But here is what makes today different from every impact that came before it. Every previous object that hit the moon was either deliberately aimed the Apollo SIVB stages, crashed intentionally in the 1970s, or completely untracked. Nobody was watching. Nobody knew in advance. The craters exist, but the impactors are unidentified. The impact times unknown. The ejector dynamics unrecorded. 2025-010D is the first unintentional impactor in the history of space exploration, for which we had the impactor's full specifications, the precise impact time, the exact location, and an international network of observers ready to watch. That makes the data produced this morning scientifically unique. And what comes out of that data in the next 10 to 14 days will matter far beyond this single event. But first, what Danuri saw. South Korea's Danuri Lunar Orbiter has been in continuous operation around the moon since December 2022. It carries 6 science instruments, including the shadow cam, a camera so sensitive it can photograph the permanently shadowed craters at the lunar poles using only reflected Earthlight. Its lunar terrain imager captures high-resolution images of the surface at resolutions fine enough to identify features less than 2 meters across. Korean engineers spent weeks calculating the orbital mechanics needed to position Danuri for the closest possible approach to the incoming stage before impact. The result: Danuri passed within several kilometers of 2025-010D approximately 2 minutes before the stage hit the surface. If those images downlink cleanly and survive processing, they will be among the most extraordinary photographs ever taken by a spacecraft. Humanity's own hardware, in its final seconds of flight, photographed by another piece of humanity's hardware orbiting the world it is about to hit. The images have not yet been released. Korean engineers are processing the data. When they release, and this channel will cover it when they do, we will have our first visual record of a piece of space debris in its final approach to an impact. What that image shows about the stage's tumble rate, its orientation, its structural condition after 19 months in space, all of that feeds directly into the models being used to predict what the crater looks like. But the images that everyone is waiting for, the images that will tell us what the impact actually produced, come from a different spacecraft. NASA's Lunar Reconnaissance Orbiter is the most capable eye currently circling the moon. Launched in June 2009, it has been continuously imaging the lunar surface for 17 years. Its narrow-angle camera can resolve features as small as half a meter across. At that resolution, a crater 20 meters wide is clearly visible in a single frame. LRO flew over the impact zone on July 29th, 1 week before impact, collecting the before image. It is scheduled to return on approximately August 12th, 1 week after impact, to collect the after image. The before and after comparison will be the definitive record of what 2025-010D produced. It will tell us the crater's exact diameter, depth, shape, and orientation. Whether it is a single crater or a double crater. Whether the hollow structure of the Falcon 9 upper stage, a thin-walled aluminium cylinder with its heaviest mass at the engine end, produced a different signature than a solid impactor of equivalent mass would have. That last question is the one Bill Gray, who predicted the impact, has been most interested in. The 2022 Chinese rocket stage produced a double crater when it hit the far side, an asymmetric result that implied the impactor had two mass concentrations separated along its length. The Falcon 9 stage is different. Its center of mass is clearly understood. Gray's expectation is a single crater, because the stage did not carry an undisclosed additional payload the way the Chinese stage apparently did. If the LRO images show a single crater of the predicted size, approximately 17 to 30 meters wide, Gray's model is validated. Hollow impactors produce craters consistent with their documented mass distribution. If the images show something unexpected, a double crater, an asymmetric ejector pattern, a crater significantly larger or smaller than predicted, the models need revision. And that revision matters, because understanding how hollow artificial impactors behave on the lunar surface is exactly the kind of data needed to assess debris hazards for future Artemis infrastructure. Here is what the impact told us that no model could have told us before today. Over 1 million kilograms of lunar soil was ejected by the impact. The plume rose above the western lunar horizon and was visible briefly for minutes to telescopes positioned along the eastern United States and South America. Amateur astronomers and professional observatories alike trained their instruments on the moon's western limb at the predicted moment. The maximum altitude of the ejector curtain was expected to reach approximately 75 to 100 kilometers. The lateral spread of ejector across the lunar surface was predicted to reach approximately 183 kilometers in every direction from the impact point. 183 kilometers in every direction. That number is the one that every Artemis mission planner needs to know. NASA's planned Lunar South Pole Base will be located approximately 2,000 kilometers from the Einstein Crater impact site. That puts it outside the maximum ballistic range of the ejector from this specific impact. But the next accidental impact on the moon will not land 2,000 kilometers from the base. It will land wherever the orbital mechanics take it. And without a tracking system for objects in the moon's gravitational neighborhood, without a requirement for operators to register or dispose of hardware placed on translunar trajectories, the next 2025-010D could land anywhere. The moon currently has no early warning system, no debris catalog for cislunar space, no legal framework requiring disposal of objects that enter the Earth-Moon system. There are approximately 35,000 objects tracked in low Earth orbit by the European Space Agency's surveillance network. In cislunar space, the region between Earth and the Moon, where 2025-010D spent 19 months, there is no equivalent. Objects appear in that environment only when civilian asteroid surveys happen to photograph them. The fact that we had 1 week of notice about this impact is not a triumph of the system. It is a demonstration of the system's limits. One independent astronomer in New Hampshire identified the trajectory because he was watching. If Bill Gray had not been watching, the impact this morning would have been logged as an anomalous seismic event, if it was logged at all. The Outer Space Treaty of 1967 makes nations responsible for the activities of their national entities in space. It does not specify what responsible disposal looks like for hardware placed on translunar trajectories. The regulatory frameworks that govern low Earth orbit, the FCC's 5-year deorbit requirement, do not extend to cislunar space. No such requirement exists anywhere in international space law. Juliana Scheiman, SpaceX's director of NASA Science and Dragon programs, said at a press conference this week that the company followed the appropriate rules and regulations for disposing of the Falcon 9 second stage after launch. She was right, they did. What happened was, in her words, essentially a mixture of solar activity and gravity forces that put it on a path toward the moon. The rules allowed it, the physics ensured it. SpaceX subsequently adjusted at least one later upper stage, the one launched in November 2025, for the Escapade mission to end up in solar orbit rather than a moon-crossing trajectory. That adjustment is not legally required. It is a choice, which means the choice to protect the moon from future untracked impacts is currently entirely voluntary. Today's impact will add a 4-ton rocket stage to a total that already exceeds 209 tons. The next 20 commercial lunar missions currently in planning across 8 countries will each add their own hardware to that figure. Without legal requirements for disposal, without a cislunar tracking network, without an internationally agreed protocol for what happens when hardware reaches end of life in the Earth-Moon system, the moon is absorbing the waste of the commercial space era, the same way low Earth orbit absorbed the waste of the government space era by accident, without records, without accountability, until the accumulation becomes a problem that cannot be ignored. That tipping point has not arrived yet. But today's impact, the first ever confirmed near-side human-made impact with advanced knowledge of the impactor, is a precise and datable record of where the accumulation stands right now. 209 tons, 3,000 objects, one new crater, one independent astronomer who was watching when nobody else was. So what happens next, and what should you actually be watching for? In the next 48 hours, Danuri's images from the approach and immediate aftermath should begin the release process. When Korean engineers downlink and process the data from the high-resolution lunar terrain imager, those images will be the first ever taken of a piece of space debris in the moments before and after it hit another world. This channel will cover them the moment they are released. In approximately 7 days, around August 12th, the Lunar Reconnaissance Orbiter will make its post-impact pass over the Einstein Crater region. The before image exists, the after image is coming. When those two images are placed side by side, we will know the crater's exact dimensions, its shape, its orientation, and whether Gray's single crater prediction held or the hollow structure of the stage produced something unexpected. That comparison is the scientific payoff of everything that happened today. Not the impact itself. The impact was over in a fraction of a second. The payoff is the permanent record it left, and what that record tells us about how hollow human-made objects behave when they hit the moon. Bill Gray, the man who found this object drifting and calculated its fate, made one observation about what it means that his prediction proved out. The motion of space junk, he has written, is mostly quite predictable. What is not predictable is who will be watching when the next piece starts moving in the wrong direction. Today, someone was watching. The result is a 20-meter crater on the near side of the moon, a plume that rose 100 kilometers into the vacuum, and the first complete dataset of a known impactor strike in the history of human spaceflight. The LRO images will be worth watching for. Subscribe. That update drops the moment NASA releases them.